you have been made to join the another portal to deliver your talk. We are very lucky to have you as a resource person for today, sir. Please go ahead, sir. Now you can. Yes, sir.
Can you hear me?
Yes, we can hear you, and we can see your screen as well.
Okay. So good afternoon to all. Thanks once again, organizer, and thanks for introduction. And I think all of us in this really very critical situation have to be very patient, and thanks to all that in spite of all some problems, we come in contact to this online mode. Once again, I express my sense of gratitude and thanks to the organizer for inviting me to deliver this talk. Just 1 minute. Hello. Yeah. I think, can you listen to me? Hello?
Yes, we can hear you, sir. Please go ahead.
Okay. So the title of this talk is Machine Learning in 5G CR-IoT Remote Healthcare Support. Instead of going in details, I will just say what is the outline. In this talk, I will try to briefly talk about the healthcare issues and IoT, how it makes, and to materialize this IoT, the promise and the potential of health support or smart health support in IoT, we will see that 5G is the backbone. So I will introduce briefly the 5G communication in the first part, and in the second part, I will talk about machine learning algorithms, particularly the GAN networks for data augmentation, medical data augmentation, and I will introduce cognitive radio multi-hop network for supporting this. That means it's a ultra reliable, low latency communication framework for cognitive radio IoT. And then I will talk about some diagnosis, computer-aided diagnosis for remote healthcare using this network or using this multi-hop network. So let us come to the smart healthcare support. What would happen? I told the other day when I was talking about cognitive radio IoT, there was an application of IoT, wireless medical applications, and there are different networks like communication technology like MICS, medical implant communication, wireless medical telemetry services, wireless body area network, and there are radar imaging and remote healthcare. So all these are currently in operations or attempts are made to make them materialize. So in that sense, what is essence is the connectivity. Now, what the benefits smart healthcare can provide? First thing is improve treatment possibility or facility. That means well-being. Second thing is the patient need not. So it's shifting from the hospital-centric to or clinic-centric to the home-centric. So patient need not have to move or visit clinics every time or frequently. And of course, a timely decision to be taken, and that reduces the expenditure of the medical diagnosis or medical treatment. And other things on the point of view of the service provider, that they can extend their coverage. So there is possibility broadening the range. So if we see the facility simplify, that what the smart healthcare support provides, one is improved treatment facility. Second thing is, as I say, the patient need not have to visit clinic or hospitals every frequently for regular health checkup, reduce health expenditure because of timely diagnosis. And of course, the service provider point of view or the business perspective, they can extend their coverage. Service provides broadening the service by beyond geographical limits. Now, when we go for IoT, this smart healthcare, IoT offers certain advantages, some applications, some facilities. What's that? Management of hospital assessment. So that's one thing. Monitoring, remote monitoring, and service assisted, diagnostic assisted monitoring. So these are advantages in IoT when applied for smart healthcare. That assess management in hospital, we have the resources and medical equipments that can be shared or managed. Behavioral change monitoring to be there, remote monitoring, as I say, that wearable devices to be patient's body, and that can continuously monitor the temperature, the glucose level, blood pressure, and all these physiological properties or attributes of the patients. That's the remote monitoring, and they need to be continuously communicated. Treatment compliance monitoring to be done, assisted living to be, smarter medication to be there, and of course the telemedicine. So that is the the situation, and I told that different frameworks. So in WMTS, MICS, wireless body area network, ultra wideband, and all the designing factors when we look for CR-IoT, that's the first things is what is the data range or what is the data rate, what the data rate to be transmitted, whether it is a low data rate, what would be the enabling technology, what would be the regulation requirement, government regulation requirement. So that factors are basically the application, what are the data types, what's the bandwidth requirement, what are the signal nature, whether it is an analog, type, whether it is an analog or whether it is digital, whether it is continuous type, whether it is intermittent type. So these are all essential. If we see the slide, this slide, which I already showed in other day, that if it is a medical implant communication services, the data requirement rate is very small, 16 kilobit per second, and 3 megahertz bandwidth is required, low bandwidth and frequency shifting techniques are there, coverage zone is 10 meter less. On the other hand, when we go for WMTS, essentially data rate increases to 76 kilobit per second and 6 megahertz bandwidth. The frequency range is 608 to 614 megahertz, and coverage zone is 100 meter. We will go for frequency hopping or type of modulation techniques. And when it is wireless body area network or ultra wideband, then the frequency range shifts towards the 3 to 10 gigahertz. And port division multiple access or multiband orthogonal frequency division, 500 megahertz bandwidth, 800 megahertz kbps data rate, and range is 2 meter. Now, question is, when there is a promise or potential of 5G, we have all smart healthcare supported. Say, for example, we can imagine the remote surgery. We can think of that vehicle-to-vehicle driverless communication. Vehicle here is the ambulance. So it's all possible, and that possibility is done because of the promise and the potential of the 5G. So in 5G, it's the machine-to-machine communication and IoT that plays the important role or pillars in the smart healthcare support. But when we look for the 5G, the two essential issues that comes into the situation is ultra densification of networks. That means billions of nodes to be connected, IoT objects to be connected, medical devices to be connected. So that is one important issue. And second important issue is the energy consumption. These IoT devices or objects are low power devices. They work with limited battery power. They work with limited memory. So this issue need to be. So in your data acquisition process, in your data transmission process, in your data processing steps, necessary algorithms to be done in such a way that it is computationally less, it is energy efficient, that it enables energy efficient transmission. So with this, we understand that there is the 5G benefits we have to exploit in order to provide smart healthcare support by means of IoT. So let us have a look from journey to 2G to 4G and what the characteristics, features in 5G. What are the attributes in 5G that makes it crazy and that makes it crazy in IoT marked healthcare supports? So if we have a looks on the 2G to 4G, and I just have a glance of representation. If we see the first generation, it was purely analog based modulation and it was only voice applications. And then we go for second generation, it was the digital voice, but no data transmission, and all this rate was very less, 10 kilobits or something like. Then we go for 2.5G, so like say GSM or CDMA like technology, 50 kilobits or 200 kbps data transmission in 2.5G, and only voice plus data, like say SMS and all this was started. And then when you go for 3G, the WMTS or wireless, wideband CDMA or UMTS like CDMA 2000, and we see that voice, data, and video calling, these are all possibilities, and data rate gradually increases from 380 kbps to of the order of 5 to 30 megabits per second. And when we go for this 4G, then LTE, the long-term evolution or WiMAX, is coming into the situation that orthogonal frequency division multiple access and data rates of the order of 100 to 200 megabits per second, voice, data, and video, online gaming, high definition television, all these are possible. But when we go for 5G, the demands are coming something different. That whatever data rates we see here in 4G, it would be multiplied by 10-fold or 100-fold. So of the order of gigabits per second, data, and connectivity should be of the order of, billions of nodes to be connectivity. Latency will be very small, near real time of the order of nanoseconds, level of this, and battery lifetime would be very high, means whatever power consumption or energy consumption in this 4G or today's scenario, that to be 10 times energy consumption reduced, or in other sense, your battery will be enhanced, lifetime will be enhanced by 10 times. So let's see the journey, I mean the road journey to 5G, and you can see that downlink and uplink data rate, what it expects. So 100 times faster than that of 4G. As I already say, that in 5G networks, if you characterize, there would be ultra connection, ultra dense connectivity, ultra reliable transmission, and means that reliability outage or would be of the order of 10 to the power minus seconds, and it will be massive machine communication. So ultra reliable communication, ultra dense connectivity, I mean machine connection, and massive machine communications. So this is 5G future. Now question comes that I put, that what 5G makes so exciting? Apart from this particular application which I will be talking here, the smart healthcare support and by means of IoT, there are also other services and all this that coming into the 5G. Now question comes, what makes the 5G so crazy and lucrative? There are a couple of facilities in 5G. The first one is the millimeter wave communications, the super highway. That means the frequency range is upper of the order of say 24 gigahertz to 300 gigahertz. And as you know, the road wider, the vehicle speed will be larger. Same thing in communication. If you go to the upper part of the frequency spectrum, that means in the hertz of gigahertz range, obviously data transmission rate should be high. So millimeter wave communication. Millimeter wave communication again other. So millimeter wave communication is one facility. Second thing is your massive MIMO. Your device will equipped with a large number of transmitting and receiving antenna that will provide the diversity and multiplexing gain. You will see there is the small cell, there is the beamforming, there is NOMA, non-orthogonal multiple access communication, and there is mobile edge computing. That is again essence for the IoT smart healthcare support. So these 6 pillars which I say already, millimeter wave communication, massive MIMO, small cell, beamforming, NOMA, and mobile edge computing. This is, I will come just one by one, what the benefits we are getting from and how it supports IoT healthcare supports. Millimeter wave communication, as I say, that it's the higher frequency range of the order of, as you see the spectrum, you will find that 1 gigahertz to 10 gigahertz and all these spectrums are heavily crowded for other services, licensed services. And this is the, this 30 gigahertz to 300 gigahertz is the millimeter wave. But there are benefits in millimeter wave, that high frequency, so large amount of data to be transmitted, higher frequency, smaller length of the wave for wavelength, and antenna size is related with the wavelength. So your antenna will be miniature. So this is the advantages of your millimeter wave communications. Antenna will be, so many antenna, large number of antenna can be equipped and more data to be transmitted. But again, there is disadvantage. I will come to this part later. But prior to that, there are massive MIMO. What it suggests, that the more number of antenna or large number of antenna, both in transmitting and receiver end, can be equipped. And by means of that, we can get benefit of spatial diversity. Spatial diversity means we can create more number of individual terminal, individual antenna can create an individual communication channel or link. So at the receiver, you should have multiple copies of the same message, and you can combine them and you can get the benefits of the diversity. So massive MIMO, large number of MIMO, I mean antenna, can be equipped in your base station or in your handheld devices. So that provides the spatial diversity. You can I like to show mathematically that when it is a single antenna communication systems, we know that capacity is B log 1 plus SNR, signal to noise ratio. B is the bandwidth. Now, when it is a multi-antenna equipment communication, so if there are M number of transmitting antenna and N number of receiving antenna, so we can get this much of benefit of capacity, this fold of benefits in the capacity. That's the spatial diversity. So this is the advantages, as I say, frequency and higher frequency. So millimeter wave enables a lot of transmitter and receiver and this. So that benefit is there. But millimeter wave has really drawbacks also, because if you see the high frequency, smaller wavelength, so when these radio frequency wavelengths are small, they will have the problem of attenuation. The rainfall, diameter of the rainfall or air particles will be comparable to that of the radio frequency wave. So what I'm going to say is that your millimeter wave is high frequency, wavelength is small, so radio wave that is transmitted, that wavelength is small, and it is comparable to that of the diameter of the your rainfall. or your air particles. So attenuation will be large, and there will be obstructions. So trees, buildings can create an obstruction. So it will not cover longer distances. So coverage will be less, or coverage will be suffered. Attenuation is high and coverage will be suffered. So that's the disadvantages of millimeter wave. So this millimeter wave disadvantage, high frequency signals, collision, millimeter wave signals will be blocked by building blocks. But this problem again can be overcome. We can go for the small cell, densified network, heterogeneous network. When we go for small cell, we can have, instead of a large tower, we can have a smaller antenna, and we can have a small cell. We can have a facility of frequency reuse. We have a beamforming instead of omnidirectional. So if there are devices very close proximity, they will be suffer from interference, and that problem can be taken care by means of small scale, by means of beamforming. So what it like to say, you can go for small cell and go for looks for small cell, which fills the coverage gaps between the base stations and the end user. And now in this case, instead of omnidirectional radiation, where it is lost much in millimeter wave, by using horizontal and vertical antenna, you create a beam. What it like to say, you create a contract, a pinpointed where the radio frequency is really required, instead of spreading in omnidirectional in all four directions. Instead of spreading your radio wave, you can create a beam by means of directed antenna, by means of beamforming, such that at the place where it is required, electromagnetic wave or RF wave to be focused on that. And that has been shown in these next slides, that by means of beamforming, we can have this facility, which is we are getting here, laser beam and invisible. So this is the facility of the 5G. And that's why we can make our transmission interference free from the nearby or adjacent communications. So this is benefits. And now coming the NOMA, there is another architecture that is coming, non-orthogonal multiple access. If you have communication knowledge, you know there is frequency division multiplexing, code division multiplexing, time division multiplexing. Means the radio resources like power or the spectrum will allocate a different user on CR modes. That this frequency channel in this user, this frequency this user, or in this time the whole bandwidth to this user, next time the whole bandwidth to other user, or by means of code we can share the time and frequency, the bandwidth. But in this is the NOMA. The resource, this is the orthogonal mode of operation for resource sharing. In NOMA, what we can do, it is another promising that two users, same frequency, at same time, at same geographical location. Listen my words, the two different users can use the same bandwidth or same channel for data transmission, situated in same locality and same time by means of NOMA. What they make use a different level of power. So by allocation of the different power, when they go to the base station, so the weak signal and strong signal is first decoded, and its interfering effect is cancelled, then weak signal is decoded. So it is the concept where NOMA provides more than one user the same resource block, that the time slots or subcarrier or spreading code or space. So higher throughput, higher transmission latency and signal cost than orthogonal. This is the benefits of the NOMA. And the final things, which is very important in our medical healthcare support or IoT healthcare support, what we have to data incentive application, we have to go for data analysis, rigorous data analysis, and using AI and machine learning approaches. That's the mobile edge computing. As we say that cloud computing is an environment or a platform, other day I say it provides different services, but the major drawbacks is your end user is far away from the cloud resources. So end user is working with, IoT objects is working with limited battery and limited power. So you need to do different app downloading, and which is again power hungry. So your conventional cloud environment offers, disadvantages or poses challenges in terms of your sort of things. They are far physically away, as I already say. So downloading, so power consumption and limited power and memory, these are the disadvantages. And this problem can be overcome by means of your mobile edge computing. What it does, it provides a facilities that apps to be very closer to the user. The computing would be at the end of the edge of the network, and that brings the distance closer to the end users. And there would be the splitting of the application. So the benefits are MEC brings cloud computing and services closer to the edge, physically closer to the user, and apt to be splitted. So some of the computation will be done in the end user, the IoT objects, and some of the computing to be done and in the cloud environment. So this is the advantages and that to be used. So this makes all attractive in every other applications that 5G promises. The same benefits can also be, these facilities can also be exploited in medical healthcare support or smart healthcare support and using IoT framework. So this is the facilities that can be. So this is basically the 5G I already told. I think I can skip these slides. So if we say that 5G based smart healthcare support, this is the environment, this is the centralized network, this is the distributed network. You can see that macro base station. You will see that small base station. These are small base station. This is the macro base stations, and there is the wired connections. There will be the D2D connection, device to device connection, line of sight communication. Here is the benefit. I will come to this part. So this is facility, D2D communication. There will be, enhanced, broadband services, and there will be your ultra reliable, low latency network. There will be wireless radio access network. So this is basically the different infrastructures. So this is centralized network, and there are millimeter wave communications. There will be small cell and pico cell, large cell, or femtocell, or network densifications. There will be body area network, like there would be your cognitive radio concept and all this. So you can see on the technology point of view, millimeter wave communication, D2D communication, cognitive radio, small cell network, or you can go for again AI or machine learning based approaches, all this. So this is the promise, or this is the scope. So if we just the same things, I like to show in the framework of requirements and technology. So the requirements is your enhanced mobile broadband services. By enhanced mobile broadband services, what I am going to say, the scenario you can think of your urban area or suburban area where we can see have the data rate. So here the whole objective is how you can improve the throughput, the capacity. Only objective is to throughput or capacity improvement, and you can imagine the scenario of urban or suburban area where you can expect that data transmission rate of the order of say 100 megabits per second, or in hotspot say of the order of 1 gigabit per second. This is the promise of the 5G. So don't, with this numerical value, don't accuse me what you are getting at this stage. Because 5G implementation promises that in suburban or urban area, you can expect to have 100 megabits per second. In hotspot, you can have 1 gigabits, or you can have greatest data transmission rate, 10 gigabits per second, like that. 20 gigabits per second per like that. So capacity, what I'm telling, say 10 megabits per second per meter square. This is the things. And so there are 4 networks or 4 communication environment you can imagine. The second thing is massive machine type communication. Massive machine type communication, what is like to mean? Massive machine type communication, you can think of a scenario like wireless sensor networks or IoT communication or machine to machine communication. Here your objective is energy efficiency. By energy efficiency, what it means? That how a less amount of power can be used for more data transmission. So by energy efficiency, like to means data rate divided by power consumption. So data rate to be high and energy consumption to be low. So that's why high energy efficiency. So energy efficiency mathematically, I like to means what? Data transmission divided by power consumption. In other sense, how we are giving power to be used for transmission of more amount of data. So in massive machine type communication, objective is wireless, scenario can be wireless sensor network, M2M or IoT, energy efficiency, and connection density. Connection density is very important things. Here you can expect 10 to the power 6 devices to be connected per meter square area. Now coming to the low latency, high reliable communication environment. Low latency, what I am going to say, I will talk about this framework in my system design. Ultra reliable. By ultra reliable means outage, means link failure for meeting target data rate should be 10 to the power minus 7. And low latency means end-to-end communication delay should be 1 millisecond, 1 millisecond of the order. So it is of the order of sort of real-time implementation. So ultra reliable low latency. The imagination or scenario is what? Remote surgery or vehicle to vehicle your ambulance when there is diverless situation, right? And next come to the situation is wireless regional area network. Wireless regional area network, what is like to means? It like to means the remote area, the rural area with 50 kilometer like coverage, where there are low density of populations, and you will be looking for that for this region of communication. And it is, you will see later on the technological point of view, if you see the millimeter wave communication. Let us start with massive MIMO, multiple input and multiple output, and 3D MIMO. I have already told in the context of MIMO framework that how the capacity, data transmission capacity improves by using the formula minimum m, n B log 1 by S plus N. All of you know the Shannon channel capacity B log. So in a multi-environment, when you have MIMO, so as I say that it helps in beamforming. So directed, radio frequency waves are directed towards the particular point where you need more energy rather than scattering. And 3D MIMO, as I say, what is 3D MIMO? That your vertical and horizontal in both directions, there will be controlling of your antenna beam, and it would be more focused. So this is the benefits. Millimeter wave communication, as I already say, its benefits, data transmission capacity and line of sight. But again, the problem is the attenuation. This is the challenges are there. So this challenge, the characteristics of the millimeter wave channel needs to be, model, needs to model. So the conventional wireless radio television channel model, like you know the Nakagami, Raisian, Raleigh, this model will not be that way competent or compatible in the millimeter wave communication. So the challenge here is the modeling of the radio mobile channel, data transmission channel. Now here it is coming the small cell, what I say already, that small cell and ultra dense network and heterogeneous network. One by one, if I say small cell, this is the promise of the 5G. Small cell means you have the smaller cell, so you can have the scope of frequency reuse. Means in one cell you are using one frequency, and a certain distance apart in another cell, the same frequency you can make it. So frequency reuse benefit you can get. When you go for ultra dense network, what you can think of, you can reduce the power, because your network, rather than a bigger coverage area and large tower of antenna, you are having small circle or small area, and you are having small power to cover the whole zone. So you can have maximum signal to noise ratio with less power, because your signal zone, coverage zone is lower. So you can improve maximum signal to noise ratio, but power requirement is less. So you can save your power, you can save energy. So network lifetime will be improved. And next comes the heterogeneous network. In 5G, there is a trend that you can have your network should be your small cell, picocell, femtocell, and macro cell. So all these are there. Now in macro cell, you can see, if you see the coverage perspective, macro cell support control panel to offer mobility and connectivity. Where macro cell support control panel to offer mobility and connectivity, the picocell and femtocell that support data plane to provide data with transport. So this is the amalgamation of all these heterogeneous, that's we call as HETNet. So small cells are not suitable by means of our wireless radio access network. Wireless radio access network, as I say, there is a IEEE model, standard IEEE 802.22 or long range communication for and it exploits the cognitive radio framework. So this is the benefits in individual level, as I say. Then there is coming D2D communication. It is another possibility in future 5G communication. By D2D communication, what it says, the short range communication, low data rate transmission, device can directly communicate to communicate. But as I said, device to device communication, their operation can be done in two ways. Let's say two IoT devices, they like to communicate, but there is a possibility that their coverage to be extended through the connection of base station. Means what I'm going to say, that one base terminal acts as a relay to include or to facilitate communication between base station and end terminal. So end terminal is far away from the base station. Another terminal can act as a relay and makes a communication between base station and end terminal. Other mode of operation is what? Now, two terminals directly communicate each other without going to the base station. I mean, bypassing the base station. So it is a direct link. So reliability improves, low power is required. So channel link quality improves, data link improves, at least latency reduced, means less time is required. So this is the benefits of the D2D communication. Now comes the cognitive radio. Cognitive radio I have already introduced that you have to go for a licensed user spectrum to be opportunistic share by IoT networks or IoT objects or IoT devices. So there should be provisioning of spectral information, uses information, spectral sensing, and there will be modality of underlay, overlay, or interwave. Somebody was asking me other day the interoperability, but I answered that this was immediately I put the question, what is the interoperability? And if it is cognitive radio framework, then your device can change the mode, interwave, overlay, underlay. But if it is IoT interoperability, that's a challenge. That's a big challenge. I will come to this issue later. And of course, a smart healthcare support to be meaningless. Actually, smart healthcare support is really, by IoT-based smart healthcare support is really at its very early or infancy stage. Lots process or lots way to go. And that's meaningful because millions of IoT objects to be connected and they will collect different data. And there is possibility of data analysis. And there is the success or failure, benefit, success depends on the use of the artificial intelligence or machine learning approaches. Now the question comes, where do you use the machine learning? Where we will be using this machine learning or AI algorithms in our 5G enabled network of smarts? Because 5G networks complicated due to network design. Why this AI is coming? AI and MI is coming apart from your data analysis, patient data analysis, or medical information analysis. As far as the network design is concerned, network topology is concerned, mobility is concerned, propagation model is concerned, you can imagine the today's scenario, wireless channel, which we think that beyond our control, it is possible. The wireless channel can be programmable. The software program is used. The particular channel we can make favorable and use for the communication. So the relevance of AI and ML in 5G comes because of network design, network topology, propagation, model, and mobility. So the question comes that unless this network connectivity is proper, unless this data is dumped to the cloud services and connection is ensured, the network will not be really smarter. So for really smarter network, we have to have scope of artificial intelligence and machine learning algorithm. Now, pertinent question comes in IoT-based ML system, where do we put AI and ML framework? Now, you see, there are different levels, these AI or ML algorithms or engines to be incorporated. Say, for example, if your rapid decision and low computation tasks, then your, if it is the questions of rapid decision and low computation, so your ML and AI algorithms to be embedded within individual edge devices, means your IoT objects. If it is low computation and rapid decision. But if it is low latency IoT services, latency means delay, end-to-end delay. If it is a low latency IoT services, your AI and ML engines to be at network edge. Remember my words, not at individual devices edge. It is network edge because you need to do for real-time computation and you make quick decision. Now, on the other hand, if you have huge data storage and heavy computation, so of the medical data, so your AI and ML to be done at the centralized systems. So that to be as the So I understand. So my latter part of the talk will focus on cognitive radio, AI, ML. So I will briefly introduce that AI and ML because I know many of you know the AI and ML, but still I will just introduce AI and ML, whatever is required for my analysis or understanding. So what is AI and ML? I mean, machine intelligence or MI, machine intelligence. What does this machine intelligence like to mean? The intelligence the way human intelligence to be incorporated to a machine. So machine intelligence means a machine machine has learning and thinking ability, like the way human learn or thinking. Actually, this question comes because the introduction of the digital computer. As you know, the digital computer is much more powerful for processing numerical data than a human being. If you see the digital computer for numerical data processing, its ability or capability is much more than a human being. But much of the information that human being captured from the society are non-numeric. So that puts a particular question: is it possible that these non-numerical data, visual data, or audible data, or other data which are essentially non-numeric nature, to be processed by computer with more or equal efficiency than human being? Is it possible the way human make decision or interpretation, machine can do? So that gives the name of machine intelligence. So means machine will think like the way human. So that. Now intelligence requires knowledge. So we have to incorporate, and human gathers this knowledge through learning. So we have to impart this knowledge inside a machine, and machine will learn from the data. If we see conventional computer operation on rule based. Whenever you do any program, you write, if this condition is satisfied, then do this, like that. So rule based operation. But in case of machine intelligence, there is no explicit programming. You will feed your computer huge amount of data, and from that data, it will model, the machine or the system will model. It will just learn from the data and improves through experience. So it extracts information from the data and works on the data. So that's basically your machine intelligence. So artificial intelligence or machine intelligence means a field of artificial intelligence, ability to learn without being explicitly programmed. So you have a kind of label data, you have a GP supervisor, you are having a model. So you just develop the data pattern or machine learning algorithm, and for new data, you just make use of that model and you make the prediction. So that I already say that methods that can learn from and make decision or prediction on data. That's basically machine. Now there are different tools and techniques for machine learnings. For my analysis, I will talk here only the deep learning. Deep learning is again a multi-level of learning, and learning is done in multiple level, and end-to-end learning is done. It's work on the structured or unstructured data. It is very powerful in learning. So this types, okay, before that I should say one thing. That's, I think many of you know in these days, the type of learning. One is supervised learning, means you are as if having a teachers and you are having a ground truth, and you train your networks, and then you feed the unknown data and you take the performance or validate the performance. You are unsupervised, means you do not have any teachers. You are studying the samples, and from there you are making classification. I mean, it's basically a clustering like approaches. So discover patterns in unlabeled data, something like that. Say for example, when in our childhood we learn the objects like apple, lemon, banana, and all this. So our parents or somebody say this is apple, this is banana. But well, if there was nothing else, if we are fed with different fruits, we can at least distinguish. Well, we may not know this is apple, this is banana, or this is, but with rigorous observation, we can, by discovering the pattern, we understand, okay, this is apple, this is food, like this. Now, third is the reinforcement learning, means it's unsupervised set of, learning, where an agent explored heuristically completely an unknown environment, and in an unknown environment, agent is fallen, and agent by heuristic approaches, by trial and error approaches, learn about the environment, and it defines certain goal or target. It has its penalty and it has some reward. So while it meets a target, it has an objective of meeting, reward maximization. So that's basically your reinforcement learning. What I'm going to say, even though I will take an example of reinforcement learning as the childhood. Say for example, in our childhood, when we start walking, our parents stand in one side with chocolates or candy, and the children start learning with an objective that reaching, with a reward that after reaching to the parents can get the chocolates or reward. So this is the reward. But on the way, they will be fallen, they will be stuck with the wall. So that's the penalty. The whole objective of the parent is what? To train the child to learn how to, how to walk. So that's the ultimate objective. And the child take policy. He or she may take obstacle and hand it and like that. So that policy such that the reward would be maximized. He or she will not be obstructed, fallen and injured like that. But I like to say another example here. If you see our human life, you can see the early days when we are having a large number of teachers, like our parents, our teachers who help us to learn mathematics, physics, and all this. So that's supervised learning, our childhood. If we see at 20 years or something like that, youth, we don't want that everybody will always monitor us. We like to learn from our own. That's basically a kind of unsupervised learning. And after that, when we go to the professional life or the family life, we are having a new environment. Even, I like to say, even if you marry your friend, you have you have all, known and everything. But it seems sometimes in the environment that your partners looks new in the new environment. Somewhat new. So it's something like a kind of reinforcement. You have to learn, you have to improve to have certain target. You have to balance your new family with old family, parents, and all this. You have to develop certain policy, apply certain strategy to meeting peace and to make peace and harmony in the environment or something like that. So it's basically kind of reinforcement. So it's my simple analogy. I just say it's nothing like that. So this algorithm, as I say, deep learning, as I say, the multiple layer of learning, unlike your other machine learning algorithms, it does not require any handcrafted features, and it is having end-to-end learning, and it does not require as handcrafted features, which may be time-consuming, incomplete, and creates overfitting problems. So that problem will not be there. And there is a possibility of end-to-end learning. So this is the difference. If you see machine learning and deep learning, so this is the difference. And it can work with structured and unstructured data. It can supervise and unsupervised way it can work with. So this is basically deep learning. And major challenge in the deep learning, the weights and the bias in the multiple layer. So basically a deep learning is the multi-layer and multiple layer learning, and that network weight and bias is the very important. There are different algorithms are used, restricted Boltzmann, autoencoder, and convolutional neural network approaches. In my talk, we'll use convolutional neural network in medical healthcare application, in data acquisition, super resolution image from the low resolution image, data augmentation, and in remote health diagnostic purposes. So I will talk about here the bit on CNN, just touch upon. Often we use CNN without bothering what to CNN and why CNN or what to CNN use. So just for the sake of that, I just used 2 or 3 slides for CNN. One is your convolutional neural network. By means, the convolution implies that a kind of kernel or a filter function you have to use, and that will apply over data. So convolution, you know that mathematically is nothing but the product and sum operations, a kind of linear operation. In linear system, it is a very useful property. So in convolution neural network, I'm not going to this because of the shortage of time, is basically the convolution layer. So you need to develop a kernel, a filter. You can say it's a kind of 3 cos 3, 2 cos 3, or any kind of image or video like signal. So it is an array. It's an array, and array is having some value, that's weight. That weight we have to develop, and we have to. So this is the convolution. Pooling layer is a kind of downsampling operations. Rectified is a nonlinear functions, sigmoid, tan sigmoid, ReLU, leaky LeLU. These are different functions you use. Then fully connected network, and there is the softmax. This is the final network layer, which will be connected to the classifier levels like that. So this is a kind of, so basically it is the pooling operation means downsampling, and it is the deconvolution and unpooling. So in here it is pooling and downsampling, unpooling, and your deconvolution like operation. So this is basically your CNN. The pertinent question comes, often we do not bother or do not justify the use of CNN. Where we do use CNN? Generally by name, as I say, the convolution is an important, those who are signal processing people or signal system people, you know It's a property of linear system theory that convolution in time or space domain is equivalent to multiplication in the frequency domain. And that's very powerful image restoration and many operations. Now, this convolution other way implies that it's huge. Where you will use? Now, if there is space invariancy, time invariancy, there will use the convolution operation. The requirement is what? Your system will be space invariant or time invariant. By space invariant, like to means what? Now, if you apply one operation for a numerical value located in one place, whatever response you will get for same numerical value, the same operation, when it's appear in other place, will produce the same result. So that's the space invariancy. There you will use convolution neural network. That's theoretically. Pragmatically, what? Now, if at least there is correlation, local correlation, neighborhood correlation, there you use the convolution. But in practical situation, we least bother. We do not, we stretch, we apply without bothering theory, we apply anywhere. So that sort of things I'm telling. What to use? Now, theoretically, spatially invariant system. Pragmatically, if there is local correlation among the samples exist, but practically no one cares and understand the theory. Applies to any matrix, stretching the definition. So as I say, so this is a classification cat or dog. It's a convolution, the max pooling operation, convolution, max pooling, repeatedly it is done, then you are having a, basically it's assigned a probabilistic value to the classifier and based on that it's a decision. So this is basically a convolution neural network. In brief I use, in my application of medical healthcare support, I will use is low resolution medical image and how do I create a high resolution image. Why? Now this low resolution image will be captured at the patient end and less number of data, and that's why less storage space required, less transmission burden. But at the receiver, when we will do decoding, when at the remote, at the other end, where the doctor will see the image, he likes to see in full resolution image. So he or she will like to get full resolution image. So I need to have a network, how this low resolution image to high resolution image can be obtained. This is one which I need to use, and I will go for another network. So, okay, before coming to this remote end diagnosis, I need to establish a connection, multi-hop networks. And here, as I say, that network topology, network design, channel characteristics, mobility, all this plays an important role. And here we have to use AI or machine learning approaches. So my first job is to establish cognitive radio IoT network for multi-hop framework. Means the patient in one end and doctor is in another end, and it is not a single link communication. It is a multi-hop communications. And we need, let's say, ultra reliable, means outage to be very small in individual link and low latency. So how do we design? Wireless channels is a very complex channel. And when you go for routing, multi-hop networks, centralized system does not need to go on. See, for multi-hop network, as you see, when you go for a computer science people, they always look for a source to end, the shortest path. But when it's in electronics communication people, the physical attributes of the channel is considered. Even if the low distance, but the channel quality is not good, there is an obstacle and you do not have a line of sight path. So your channel is not good. Even if the physical distance is small, the path is not good. So your channel is not in good condition. How you can get this channel state information? How you can allocate communications power? How you can develop routing strategies such that you can have a good channel or good link, low delay and maximum data transmission, and outage or link quality should be good. So this is completely an unknown environment. Your wireless node, IoT objects are agent. They need to establish connection with peer nodes. And these wireless channels are completely complex and unknown environment. It's something like you are in a new place, completely unknown place. And by trial and error, you have to gain experience. Your IoT objects in a wireless network, radio mobile network, when there is a mobility in IoT objects, the channel link is completely complex and unknown. You need to develop a link or end-to-end link such that delay will be small and quality of the support or outage will be very small. How do we develop this? we explored the knowledge of the reinforcement learning. This picture, you can understand this dog is a agent, and this environment, you see this man might have food in one hand and in another hand is stick. So it has to learn from this environment, because it does not know whether this will use this one or the food in other. So there will be X reward and large number of times action and reward. So penalty, it may be penalty also by beating by a stick. So that large number of observation, like that way it will learn. And that is your reinforcement learning. So reinforcement, what does it like to mean? That establish or increase the pattern of behavior by several tasks. A method of machine learning where an agent input to an unknown environment like your IoT objects, it does not have any knowledge about the link of the communication channel. It has to understand about the channel link. And for a certain data transmission, it may have to use more power or less power. More power means it is a penalty, less power it means reward. Or delay is more or delay is less. So some reward or punishment. And how does it do? In reinforcement learning, there is two terms. One is called exploitation and exploration. Exploitation like to means that whatever knowledge you have, you work with that knowledge. That you try to heighten your reward with that knowledge only. Exploration means you like to go for earning or gathering new information to enrich yourself. Something like, say for example, you are taking preparation for a competitive exam. You are looking for books. More and more you are books looking for. You are exploring more and more books. That is fine. But again, if you do not go through the books, your knowledge will not be developed. So there is a trade-off between exploitation and explorations. You have to have a factor. So RL is all about taking some that I already did. So in this exploration and exploitation example, I give better understood by this example. Let's say there is a fox and there is a tiger. So this fox is agent, the tiger is the opponent, and there is a cheese or there is meat or something like cheese. So if you see that there is a fox at one end of the room, and if it is somewhere here, if it is happy, it does not explore much. See, if it comes over here, there are large benefits. Penalty, reward is much more. But penalty is, it may have a chance of eating by tiger, eating by tiger. So if the fox decide not to move and stay here, means it's only exploit. Whatever it's have this stage, it is happy with that. It be happy with that. Now, if it explode, if it comes over here, there is a penalty as well as there is a reward. So it is something like this discount factor gamma, which is something like exploitation and exploration. If you have gamma value large, closer to 1, means you are exploring more and more. And if you have gamma value small, means you are happy with this current reward. So this is basically your exploitations. So you have to have a value of gamma for your typical values. Now, in my objective is ultra reliable, low latency link establishment. As I say you earlier, that our objective is to provide a long range coverage. Say your remote healthcare support. Your patient is at one end and your doctor is at far end, and this information to be transmitted over multi-hop networks. And that to operate with primary user and secondary user in a share mode, means your IoT is a secondary network, it will share the frequency. As you know, in our Indian context, there is no dedicated frequency for wireless medical telemetry service communication. There is one frequency that is actually assigned for your, what I would say, your Earth satellite communication systems. The frequency range is 402 to 405 megahertz. This is actually assigned for Earth to space communication in Earth exploration satellite for meteorological or meteorological satellites. So meteorological satellites for and that has been given for in WMTS for in an unlicensed manner. Understand what I'm going to say? Let's say for we like to develop wireless medical telemetry services. Now, what frequency we will use? The frequency 402 and 405 megahertz, if we use, that frequency is already assigned for meteorological or Earth satellite communication purposes. That means Earth to space communication and Earth exploitation satellite. And that frequency for WMTS purposes, one can go for your unlicensed manner in an opportunistic manner. Now, your IoT objects form a multi-hop network with some topology. And I will show that how a topology, configuration of topology plays an important role in the computational complexity associated with this. Now, node needs to connect it for data transmission, but this node have limited power. So it has to two requirements. Node needs connectivity, so it needs a channel, and it needs data transmission, so it needs certain power, and it has limited power. How do we solve this problem, connectivity? By means of cognitive radio. Means we will see that at this time, whichever channel is free, and from that channel, one channel or some channel to be assigned to the nodes. So source to destination, there are different relay. Each relay, when connect with nearby relay, it needs one frequency or it needs one channel. And that channel to be sensed, because it is not the free channel for this particular job. This is rather assigned for some other jobs. And we are using it, we like to use it in an opportunistic manner. So we will be looking for sensing, or somehow we will have this spectrum information, available, non-available information. And we will go for energy crisis problem. So energy harvesting will be there. That means the nodes, IoT object will harvest energy from the other radio frequency sources or other non-radio frequency sources like wind energy, solar energy, and others. So action is what? Now license spectrum is free or not. So spectral sensing, CR node and IoT objects either will transmit data or harvest energy. We need to go for cooperative communication because our transmitter, I mean the source and destination cannot reach by one hop because the link distance is so high or link quality is so poor that power is not that enough. So to provide you that, link quality or data transmission rate. So there will be couple of relay or couple of nodes, they will relay, and that forms a cooperative communication. So relay-based multi-hop wireless communication. Now relay or IoT objects, here relay is your IoT objects. These IoT objects has no knowledge about the communication channel. So it has to learn from the environment. So in my reinforcement learning framework, if I like to establish this communication problem, path setup problem, what is my objective? Now, node will harvest energy from the other RF source. Node will make, or IoT object will make energy efficiency because my low, ultra reliable and low latency outage to be, means link quality should be good, and we would have low delay. So my IoT objects or nodes are agent. This radio environment is the free space. Relays are state, means one state to say, because you do not have any model of the wireless channel. You have to learn it by Q routing. Actually, Markov decision model, I do not have scope of talking about this Markov decision model. I had in my slide, but I discard them because of the shortage of time. So in RL networks, there is a learning called Q routing. It's something like a memory like. So you can have a Q matrix and you update that Q matrix by learning algorithms. So basically, how you Q learning so can be helpful in CRA. I like to show a typical environment. So this is the primary user and this is the primary receiver, the primary transmitter. It's transmit its data. Now this primary transmitter has its primary receiver also, but these are licensed user. Now we like to develop a cognitive radio multi-hop network. Forget about this transmitter. Only thing what is, I don't show in my network the primary receiver because this is not my part. Only part is primary. I have to sense whether primary is transmitting or not. So that's why I show all these link data transmission in that these relay nodes will sense before their transmission whether it's primary transmitting or not, whether it's channel free or not. So the secondary network or your IoT medical telemetry services networks, WMTS networks works on time share based on time framework. What it will do? First, it will make sensing. How it will do? Now, all these relays. So, it is your secondary transmitter node, means secondary source, and this is the secondary destination. This distance cannot be covered by single hop. So, this is your primary receiver. This is your primary receiver. So, this primary transmitter is transmitting to the receiver, and there is a relaying on this. But we are interested about to establish a multi-hop network for this secondary source to secondary destination, and there are multiple relays. An individual link quality we will consider. So this is, if this link is poor, certain data transmission rate cannot meet, we call it as a outage. So this will be again another link outage. There will be another link outage. Now, if any one of the link falls, poor link, the whole communication process will be disturbed. Means whole communication channel, source to destination, will have poor quality. So what I'm going to say here is that we have multiple individual link. We have to look for the outage. Again, I'm telling what is the outage. Now, each link has a certain data transmission capacity, and you have a target data transmission capacity. If your data transmission, if link's data transmission capacity falls below the targeted rate, then outage. Then it is outage. So your objective would be, your power should be in such a way that your data transmission should be above the targeted rate, meet the targeted rate. But when you increase the power, your battery will be limited. It will create interference to other communication also. So your battery will be drained. Your network lifetime will be poor if you increase the power for improved reliability in the data transmission. And high power will create interference to the other communication also. So you cannot go high power. So your issue is, what would be the power in the relay node such that you should have a satisfactory link from source to destination. And that satisfactory link, which I'm telling in qualitative term, to be quantified by outage probability. How do I calculate outage probability? Now we will calculate individual outage probability, and thereby we will calculate that the worst one is the best for the overlink. So we will have a mathematical definition of this outage, and we will be looking for energy efficiency. So main objective is what? Our main objective is outage to be minimized. Overall source to destination link outage to be minimized. What are the constants? Now, I am working my IoT CR network for WMTS or wireless medical telemetry services. It works. It will not hamper the primary user. So it will first sense, and that sensing to be characterized by probability of detection and probability of false alarm. So it will meet a probability of detection greater than a certain threshold and probability of false alarm below a certain threshold. So it is the protection of the primary. Second thing is what? Now, if misdetection, means if there is primary user, but secondary misdetected and start transmission, its power should be in such a way that its interference will be below a certain limit to the receiver. Because if the interference of this is more, then this communication will be hampered. So it will not receive its own data. So interference should be below a certain limit for individual relay. All these relay do not have any scope of power from the other sources, external sources. These relay IoT nodes have no scope of, say for example, you are developing WSN-like system and your nodes have no scope of recharging from the external sources. What it will do? It will harvest energy from the radio frequency signal. So energy harvesting are there. So how the system operates? Now, before in this time frame, in this slot of the time, all these relay receive the primary user transmission and makes a global decision whether it is primary transmitting or not. If it finds that the primary is not transmitting, it broadcasts this decision to all relay that okay, you transmit because primary is not transmitting now. Then if it finds that now primary is transmitting, so it broadcasts the news, okay, primary is transmitting, you can harvest your data with this energy, you charge your battery, harvest energy. So what's the operation? Now operation time frame has two parts. Spectral sensing. At the first stage, all these relays, all the secondary IoT objects capture the primary user samples, send these samples to the fusion center, a centralized system. Because individual decision may not be reliable. So they send their sample data to the fusion center. Fusion center makes a global decision whether primary is transmission or not. I mean, operation is done or not. It makes a global decision. And if decision in hypothesis 80 means primary is not transmitting, they broadcast all relays that you start transmission. And now they follow a multi-hop link. They need to establish a link first. And once the link is established, they then transmit data. What is the required? Now, energy efficiency. By energy efficiency, what we like to say? That my link establishment should consider two things. What delay would be less? That when source to destination link will be there, delay will be less. And energy efficiency means less power will be required for transmission of more number of data or large data. So this will consider. So my relay, I mean this multi-hop network, this reinforcement learning, as I say, we need to have a reward function. What is the reward function for this case? Now, weighted average of energy efficiency. I want a link, my link to be established this path or this path. How my network topology will be there. How the IoT object to be deployed. What would be the topology of the network. And how the path to be established. That again, essentially determined by the reinforcement learning. So, reward function is here, the energy efficiency. Energy efficiency should be high. By energy efficiency high, I like to mean what? Less power for more data transmission and delay to be minimum or delay to be less. So I need to have a reward function which will consider the issues of energy efficiency and delay. Now, if you see energy efficiency issue, energy efficiency is large value required and you will be definitely requiring for delay low value. So you are having two attributes. One attribute is energy efficiency for which you want high value. And for other one, the delay, you want low value. So your reward function, so let me come to this slide first. So let me define your objective function. What is the objective function? Now you minimize the outage. Minimize the outage. What is this? Now we consider a physical channel and that's a relay fading channel and it is exponentially. So this is our outage probability of individual link. There are n number of links. So I is equal to 1 to, so sorry, this would be I is equal to 1 to n number of links are there. And this is the outage, means it fails to mix. Now for all path successful connection is outage of individual -1, means if link failure, 1 minus the total probability. As we assume the link are independent, this link is no way related with this. So the total probability is the multiplication of the individual probability. As you know, if there are multiple independent events, the total probability is the probability of the individual on it's multiplied. So this link and these links are independent. So outage of this link, outage of this link, outage of this link, when you multiply them, this would be the total probability of the outage, end-to-end outage. And 1 minus this outage is the successful delivery. So that's our requirement. So you go for a minimization of the outage, subject to what constraint? Now primary to be protected. So my sensing should be reliable such that the probability of detection should be greater than this, probability of false alarm is this. As I say, if there is misdetection, IoT objects should not hamper the data transmission of the primary transmitter and receiver. So this would be below interference should be below. So interference due to relay should be a below limit such that in primary receiver, this would not be objectionable. So their data transmission power should not create an objectionable interference at this point. That's the requirement of this one. And outage, individual links, as I say, okay, you must be happy that link not outage. But outage is what? Certain data transmission rate to maintain. Now, if your data expectation is low, outage will not be there. But you must have to have a good data transmission delivery. So large data transmission delivery. So that's why you should have individual data transmission rate, and that's your outage. Means target data rate should meet above a certain limit, and there should not be any outage. So this is the target data rate below above a certain rate. So individual route should have certain data rate transmission, and this is the energy causality. Very important things. As I say, your IoT objects will be equipped with energy harvester circuit. It is unfortunate that these IoT objects should not have any scope from the external recharging. It will recharge themselves. Node will recharge themselves from this radio frequency signal or other solar signal or other wind signal or like that. So what this energy causality mathematically like to means that whatever it will harvest energy, that harvested energy must meet the requirement of energy for sensing and data transmission. That means the relay or the secondary node or IoT objects will do two things at least. One thing is it will sense the primary user transmission, it consumes certain power, and it will go for data transmission of the medical data. So it will data transmission needs some power. So the whole power consumption must be made from the harvested energy, and that is shown like this way. This is the harvested energy, and initially it has certain battery, and its battery has certain fraction residual. So this energy must always be greater than for sensing energy and data transmission energy. So that's your constraint optimization. And we do this constraint optimization. Our design variable is what? Up to what extent we will go for sensing? Because our sensing duration should be such that it will be reliable. It will not create obstruction. It will not hamper the primary transmitter. Now, if tau is larger, this data transmission slot will be small. So data transmission will be less. So tau is small means reliability will not be there. So it will not protect the interference of the primary user. So that's why tau is a design issue. Means what would be the sensing duration for IoT objects? And second thing is what would be the relay power, PI, the power of the individual relay P1, P2, P3. What is the link power? That's the one thing. And second thing is harvesting energy. Means why? Now, a part of the received energy is harvesting and analysis. So this is a fraction which one to be used for this transmitting and all this. So that's basically your the design variable one has to go for. So first you can do classical optimization approaches to find this value. Once this is, we will incorporate the RL network, reinforcement network for establish the link. So end-to-end reliable data transmission, relay, action and reward. So this is the basically, as I already say that wireless channels are basically the complex channel. We do not have any knowledge, statistical characteristics. So we have to go for your reinforcement queue routing based algorithm, queue table to be improved, updated, and like that way this. But the important thing is what is the reward function that I need to say. As I say that end-to-end and this. So reward function for each state and action based on certain state and action. What is the state? State is nodes and action is the link from one link to another link. So what you need to do, as I say, the reward is you need to go for energy efficiency. This high value is desirable. Why do I know normalization? Because this is very large value and delay is very small value. So we need to go for normalization in between 0 to something. So it is a weighted factor. Certain weight of normalized energy efficiency and 1 minus this value of normalized delay. Remember, I use a negative term. Why? Because I want a large value of this one, but low value of this one. So I have to have large value of this negative value. So this is the reward function. Now what is E? As I time and again say, E is what? Now this is the data transmission rate. You see this is the power, this is the bandwidth, this is the signal to noise ratio, physical channel characteristics. I consider this is the power, this is the distance between the link, this is the exponential, the link quality indicator, and this is the additive white Gaussian noise channel link. So this is the basically that many number of links lambda I. So this is the signal to noise ratio, and this is the total energy consumption, spectral sensing energy consumption and data transmission energy consumption. So this is basically energy efficiency, and you see the delay. What is delay? Now data transmission divided by rate. So this is corresponds to the delay, and this is a, as I already say, that the network topology has a role in reinforcement learning. If we have a fully connected network, means all relays are connected with other relays, then it is a, for n number of nodes or link, you have a computational complexity of the n cube, right? You have to go over exponential searching for path establishment. If you have a rectangular grid-based structure, it comes to the runtime complexity n square. If it is a square grid-based like structure, you will, rectangle and square, you can understand, I think. So it's something like this. Now, if you have a T-structure based network, it comes to the linear form of this exponential. So you can say that network topology, when you establish, as I already say, network topology, and that's the relevance why AI or machine learning algorithm is to understand, to make the network much smarter this is the use. And I typically show an example of this. This paper was published in our IEEE transaction on vehicle and network. This is last year it was published, and this is a typical application for ultra reliable low latency communication networks. With this, once the path is established, now I will come to the latter part of this talk is basically the I think I don't know whether I will go for the time of taking all this. So this is basically your compressed sensing data acquisition healthcare. So I will be talking about data acquisition framework, and then two application. One is the how low resolution image to high resolution image for data, augmentation purpose or for diagnosis purpose. And second thing is end-to-end. By using this end-to-end data path, how do we provide a kind of diagnostic, AI-based or machine learning-based diagnostics. So two things I will be talking about. Now, one thing I say, if you just recall, the current mode of data acquisition, basically all are digitized mode of application. So your analog data is digitized. Now, when you go for digitized, you must have to follow an Nyquist sampling rates. All of you know that sampling means it must have to follow the twice the highest bandwidth or the highest frequency present. But all we know again that in digital data, there are lots of redundancy. So we go for compression. So you see the current mode of data acquisition, two things you are getting. So let me first in the CR-IoT framework, that current mode of data acquisition, there is high rate of data sampling you have to take, and later you will throw the data because there are redundancy. Means sampling first at high rate, then you do compression. The pertinent question comes, if I have to throw the data, then why don't we throw right at the time of data acquisition or capturing of the data? So data acquisition compact for storage and transmission. Volume of data transmission has a role on storage and impact on delay. IoT objects do data sensing and acquisition. So what I'm suggesting here, a technique that's called compressed sensing, some of you might know what it says. Now, why first at the high data rate sampling and then throwing? Then why not throwing it at the time of data acquisition? That's called compressive sampling or compressed sensing. Means you sense those many data compactly, which is essential for this. So basically, it is a mathematical problem. What does mathematical problem? Okay, so we'll talk this problem in the framework of convolutional neural network. So as I already say, high rate sampling and then compression. But we have n number of data. Basically, we throw redundancy due to, and we work with m data. So of course, we do rather later decompression from m to n. Now the question comes, if the question is, if I show pictorially, first we do the sampling and then compression. Then why not together couple compressed sensing? Means sampling that a compression right at the type of sampling. Mathematically, this is a problem which is an underdetermined problem. Like our school day mathematics, if you are given a two variable unknown, and if you are given one equation, suppose x plus 2y is equal to 5, and you are asked to find x and y, you will not be able to find because you have two unknown and you need at least two linear equations. But you can find infinite solution. Take one variable value from your own, and putting that value, you can find other value. So it is an ill-posed problem, underdetermined problem. Theoretically, you have infinite number of solutions. Now, if your application say that out of this many solution, a best one for your current objective to make, you can take, that is okay. So it's basically an underdetermined problem. So what I'd like to say, mathematically, you have an endpoint data. Forget about this signal processing approach, as the computer science people or others might be there. For them, I am saying, what the problem? The problem is I have actually an n data point, means x1, x2, x3, xn number of data. But somehow I captured data ym, ym, y1, y2, y3, ym. M is very, very less than n. So from this m point data, I have to go to n point data. And for that, I have a convex or sort of optimization problem, constraint optimization problem, and I will get, right? So this is basically my compressive sensing or compressive sampling. So for its operation, it needs signal processing two property. One is called sparsity, means in original domain, suppose you are shown a medical image. From the original domain, you cannot compactly represent it. You cannot throw it. You go to JPEG compression, you go to MPEG compression or JPEG 2000 compression like that. What do? You do some DCT. So your image from original domain to compress or transform into DCT domain, you decorrelate, and some of the coefficients are so small value, you throw them. And then you do the decompression. So that's the sparsity. By sparsity, what is like today? So your data acquisition to be done not in the original data domain. You create a projection space, and from there you capture your data. It is possible your network, your sensor to be designed like that way. It will not capture data in the original domain. It will project it in a transform domain or in a projected domain where many of the coefficients will be very small value or zero value. You can throw them. That it is done in your FFT or DCT, discrete cosine gamma or Fourier transform. And you take the samples randomly in coherence. So your sensing or sampling domain and presentation domain should be in coherence, means uncorrelated. I'm not going to details in all this. So mathematically, I like to say what it is basically. If you see this picture, it will be understood. It is your original data X. See my mouse movement. This is the original data, M point data. Let's say it is a Fourier transform, size Fourier basis. So you do the Fourier transformation, and that's your Fourier coefficient. This is your endpoint data, because your X1, X2, Xn data, when you do the Fourier transform, it is endpoint data. But the interesting thing is some of the Fourier coefficients are very small value. So it is only k number of data which are non-zero. Rest are all zero or very small value. You can throw them. So it is basically sparse representation. This is a sparse representation. Now from this is you are having a phi. Phi is a matrix. You are having a random sampling. You are from this data, you are randomly sampling few data. So if it is M point data, so essentially it is a M cross N. Your S is an M cross N vector, and you are having an N cross M vector. So it is so basically it is a N point data. After Fourier transform, it is an N point data. So it is N cross 1 data. It is an N cross 1 vector, and you are having a matrix, two-dimensional matrix, which is M cross N. So when your M cross N multiplied with N cross N, it becomes an M cross 1. So you are essentially captured only M data. You imagine it is nothing but a matrix, M cross N matrix. So your Xn, X1, X2, Xn data, you are having a Fourier transform, N point Fourier coefficient or DCT coefficient. You multiply with M cross N matrix, random matrix. You pick up those random values, M point data. So from there, you like to go back to in. Now, if you say that you multiply, this inverse operation is not actually the exact solution. If you go by M point to this way by reverse, you do not have the exact solution. Your solution should be based on, you are essentially from low value to high value when you go infinite solution. For your targeted application, one solution would be the best, and that you do. And that's your basically the convex optimization. But when you do spectral compressed sensing based data acquisition, you have to look for a parse domain representation. You have to do computation, convex optimization and all this. So exceptional computation. So signal needs transformation like DCT, all this, LP norm optimization. So large computation. We like to say that this is possible from the less number of data point or subsample data point to high. As I say, architecture, you can see the convolution neural network architecture where I saw this one, basically this one, this structure, if you see, yes, I can go for larger space to lower space and from there inverse operation like that. So that's possibility. I'm not looking for parts domain representation in original transform domain. I'm not doing LP norms minimization and all this. And that I'm doing exceptionally. So I have a low resolution image and I like to go for high resolution image. X-ray tomography, ultrasound, radar imaging, MR imaging, reduce computational cost. So you are having always super resolution image required. But your data capturing, because your IoT objects having limited memory, so it will capture less data. It will transmit to the data center, and data center will do this all computational job and generate the super resolution image, and doctor will diagnosis for that. So we use here a GAN network, generative adversarial network. You might know this generative adversarial network. There are two networks. One is the discriminator network, another is the generator network. So basically, the analogy is something like that. Somebody likes to generate a fake currency. and police is there. Police is a discriminator. So who like to generate a fake currency, his strategy should be the currency, generated currency should be as closer to the original one. And police has to discriminate it that this is not original, this is the fake. So the police will defeat when it will be in a confusion that half of the time it will be probabilistically it is the actual one or it is the fake one. So it is, if its confusion is maximum, the discriminator will be success. So there is a tug of war, there is a competition between generator network and your discriminator network. So what it is, it's an autoencoder convolution neural network model. Suppose this image we like to generate full resolution image. What we are doing, we take the subsamples by convolution and pooling. So this is your sensing networks. And then we add noise because there will be some noise also during the data acquisition or transmission process. So this is basically your compressive sensing. Now what we are doing, it is your generator network. So this is your sensing network. This is your generator network. This generator network do the reverse operations. So unpooling, deconvolution and unpooling. Now whether it is a good one, actual one or not, a discriminator will discriminate it. So it will classify it as a original class or not. So the whole network will act like a autoencoder. So it as if generate this one here by means of generator, and discriminator likes it basically as a teacher. It's like a clever approach of unsupervised. It's basically GAN operates like an unsupervised approach, but discriminator networks like a teacher. It's just clever approach that this is not good generated. So you improve. It asks generator, okay, you improve because your generated one is not the actual one. So it will discriminate like this way. So this is the one I did not. So this is basically data augmentation. Basically, it is required for low resolution to high resolution for remote end diagnosis, or sometimes you have less number of medical data, but when you go for AI and ML algorithms, you have to go for data augmentation. You can make use of this algorithm. Now I will talk about a particular application for pneumonia detection. I think I have to quickly finish by 5 minutes, so that we have certain discussion on all this. So deep learning and compressed sensing measurements in pneumonia detection. What we say that we will capture less amount of data at the patient end by means of compressive sensing theory, but actually we will not do compressed sensing. We will make use of the convolution neural network for generating this subsample data, and that subsample data will transmit it to the radio mobile channel, which that radio mobile channel we have make use that CR-IoT network. That's multi-hop network we have by means of that. And at the receiver end, we will have two options. On that low resolution image, we will have a discriminator, we will have a diagnostic or classification network, and we will have a full resolution image reconstruction so that our doctor can diagnose. So we have two provisions at the receiver end. We will have the original low feature space data, and our classifier will work on that because it will simplify the computational job, IoT objects. And again, when it is a question for the doctor diagnosis, he needs or she needs full resolution images. So as I already said, pneumonia is a basically fungi or bacteria or like a disease, a common life-threatening disease, and doctor prefer the chest ray images by means of X-ray imaging, and diagnosis needs the radiologist at the patient end. But in our country, this imbalanced number of patients and doctors, or in as far as the WHO reports, the 2/3 people have no radiologist today. So we look for a CR-IoT framework where low resolution data to be captured at one end, and it will be transmitted over this multi-hop network, and at the far end there will be diagnosis as well as the reconstruction of the image for patient, the radiologist diagnosis. So automated diagnosis, computer-aided diagnosis, and human diagnosis, that provisioning to be there. So what we need, a full-scale X-ray image to be done by means of convolution network, and that's promising future IoT services. Its bandwidth and energy efficient transmission. Train to, and now another issues, how our network take care. See, in communication, it is the power basically essential for MAC layer in order to have a reliable data transmission based on the channel link. But again, channel information is a very, very outdated channel, and on the communication people really face problem about the channel link or channel quality. So here this convolutional neural network or machine learning algorithms just take care of this power allocation based on the channel link. So this multiplicative or fading effect and the adversarial, and the noise, additive noise effect is taken care of. So mathematically what I say, this is our captured image. This is the radio mobile channel, multipath channel, This is the sensing matrix, linear operator sensing matrix. So your capture data is captured. So this is the low resolution, image, and this is transmitted over a radio mobile channel. This is the radio mobile channel feeding channel, and this is the additive channel. So your radio mobile channel is contaminated by two types of noise, multiplicative noise and additive noise. So this is basically your received signal is coming over. And theoretically, this is a convex optimization of problem like this. This is an objective, and this is the constraint optimization. This is basically a trade-off factor. I'm not going to. What I'm going to say, if we use the conventional approaches, we have a lot of competition and all this. How our neural network, our convolution neural network take care of this? Same thing we have. So it is basically your X-ray images. It is your network which gives you the measurements, and this convolution neural network, this is a classifier. So it's basically classify whether it is a pneumonia or non-pneumonia, and it is a network, another network which regenerates this image, and this will be used by doctor. Remember, we do CAD diagnosis, whatever less number of samples are transmitted using that, because that makes our diagnosis faster. Rather than going back to these and then doing diagnosis, there are approaches in the existing literature where the people get the full resolution image for CAD diagnosis. But here we make CAD diagnosis over these less features, small number of data, and at the same time, we reconstruct the full image so that it can be diagnosed by the doctor. So this is done by CNN networks. And so this is the architecture of the classification, 3 full connection and convolution network. I think this is absolutely network architecture. Different architectures, the activation function like sigmoid function as the classifier. We use the sigmoid function, and internal stage, we have used the ReLU, leaky ReLU or network, because we have the data value from negative to positive. So in order to make use of this, we have make use of the negative ReLU. I'm skipping all this. This is essentially not. It's also classification problem. This is ReLU network or leaky ReLU network. It can be used. So this is basically the loss function in terms of epoch, the training and test, validation accuracy in terms of the loss function. This is basically the loss, and this is the accuracy. And the benefits that we get here is that the prediction accuracy, 20% measurement. Imagine in your full resolution image, if you have only 20 data, let's say 20% data, means your image is 100 cross 100. Now it's 20% data if you are available, with that your diagnosis, the proposed model give the accuracy 95.2%, 22%. If the 40%, percentage measurements, or if you have 40% captured data, accuracy is this much. Now you imagine, instead of using full resolution image, your diagnosis is only 20% data, 40% data. Lot of savings in data storage, computational cost, and your transmission bandwidth. So these benefits we are getting. So that is with respect to the accuracy in the benefits of this. This is the results. I skip all this. Now challenges, IoT, I will finish by this. As for example, sorry, I'm going late. So one is the achieving interoperability. Somebody asked me this question, but in case of IoT, this interoperability is very, very challenging issues, because millions of devices, different protocols, and different standardization. There are lack of communication, universal communication. There are LoRa. LoRa, they have standardized wireless, LoRa wide area network. Basically, LoRa is a kind of speed spectrum. Those who know the low power modulation techniques based on the charged speed spectrum. So that can be used. Sigfox is used for coverage area to extend it. So this is a challenging issues, interoperability. Big data, it is very, analysis of this is very, very essential issues, because all you know that there would be user information or the patient information, patient psychological, physiological information, billing information, and lots of data to be there. So that's again an issue. For that, one has to work with. Then performance of connectivity. As I say, my whole talk was an important issue of connectivity, how ensures the connectivity. Connectivity will be, again, there are two things. One is the high mobility, moving patient, high speed ambulance. Connectivity, again, on the rest of short or small range. Then the more important things is achieving secrecy, trust, or privacy. That is a very, very important thing. And your algorithm should have secure and straightforward communication that will ensure the security between smart healthcare devices and cloud database in an authenticity and integrity manner. well-defined approaches to provide risk assessment. It will detect the upcoming or the present attacks, or there will be strong privacy policy that must be provided so that it can approve the new user and trust it. So this is all the issues as far IoT framework perspective. Other issues in the machine learning, and say, as I say, low resolution to high resolution, we can look it for extended for region of interest and can be extended for tumor, cancer, or kidney diseases. We can go for multi-layer, multi-level transfer learning approaches for diagnosis of the rare diseases and all this. So this is all. Sorry, I'm running late. So this is all this. I finished. I don't know. There are any time or time. So if you have any question, please.
Yes. Please. Thank you. Thank you very much, sir.
I'm sorry. Actually, I took much time.
No issue, sir. No issue. Thank you very much for your lengthy talk, and where you have covered all the aspects from machine learning to deep learning to reinforcement learning, and that is the transfer learning as well. And even you discussed the latest one, the Q learning. So nice, sir. Thank you very much for your kind support to us. And I request to the participant, if they do have any question, now they can go ahead with the questions. And one more information to the participants is, so Meet is now okay, it's working now properly. The next session we will be conducting on the same Meet link at 3 o'clock. So right now, if you have any question, please go ahead with this. Please go ahead.
I'm sorry, actually title of this topic, talk is machine learning, CR-IoT. So it needs introduction of machine learning and two different approach and communication to support 5G and all this. So it takes much of time for deliberation. You may be again bored with all this stuff. But as it is a faculty development program, my objective was just to give some flavor or multidisciplinary flavor to the faculty members, if possible to integrate, because whole this approaches CR-IoT, or forget about CR-IoT, IoT application specific, IoT medical healthcare, it's essentially involve the multidisciplinary framework. So I like to give different topics and how they can be synergistically integrated, and that was my objective. Sorry because of this too many stuffs, but I like to give that how the teachers can link while day-to-day teaching or in research problem, the diverse field or something like, and integrate and formulate the problem. That's my objective. I don't know, how much I'm able to do. Okay. So any question, I would be happy to take. Because I cannot see any chat box sort of things like that.
Yes, sir. Yes, sir.
So anybody can directly ask questions.
Yes, sir. And for your talks, sir, no need to say sorry, because nowadays talks cannot be talks are really interdisciplinary. We have to speak a lot of things which is related. So your talk was up to the mark, where you have correlated all the things which is the right, which are rightly required for the research, today's research. So your talk was ultimate, sir.
But I don't know, because there was no interaction from the audience thing. So maybe they feel bored.
Hello.
Yes, sir.
Yeah, sir. Actually, it is a very nice talk, and we receive a lot of appreciation from the participants for your last lecture as well. Actually, now this just a minute, please. So because of some problem in this Google Meet, so the participants, they got very exhausted, as well as they were, in fact, now we are waiting for the next session to be shifted on to Meet again. So it is in fact very nice, and I would like to request you to join this valedictory session at 5.
So how do I join? How do I join? Should I be?
Yeah, the same thing. The Google Meet.
Or if I can keep myself online like this way, I can directly join like that. Is it?
Yeah, you will be joining with the Google Meet. The link that has already been given to you.
So valedictory program to be done in the Google Meet, no?
In Google Meet.
Oh, and so I can go out of this. So I can leave this meeting platform like.
Yeah. If there is any change, we will be communicating to
you. Sorry. Actually, this was the email was sent related to this, but I could not see this email. So that's when I go for joining, I came to know this.
It happens with us.
Actually, Professor Lolit Singh Sharma sent me an email at sufficiently ahead of time at 12, but I didn't see it. Sorry, I'm sorry. That means,
you saw it, and that is why we are able to conduct this session. And I will be very happy inviting you as a guest of honor in the valedictory session, sir. So please join.
Thank you. So I think there is no question this time, no?
Yes, sir.
Okay. So once again, thank you to all for your patience, and thank you, organizer, for inviting me this talk. Thank you so much. Bye.
So we are ending this meet, sir, right now. Thank you very much. Let's meet at valedictory. Thank you, sir. And the participant will join at 3 for Google Meet, same link. Thank you, sir. Thank you. So nice.
Thank you. Bye.